Okay, finding areas, another approach to finding areas. And this one, we're actually going to learn how to find the exact area instead of using Riemann sum skewed approximations. And the way we find exact areas is actually through antiderivatives. So let's revisit antiderivatives a little bit. Up until now, I've always just called them antiderivatives, but they are actually integrals, and they are indefinite integrals. So if you see an an integral sign that does not have limits of integration, then that simply means to find the general antiderivative of f of x. So we're going to change our notation. When I want you to do an antiderivative, I'm going to write it like this. So example number 1 here, if I want to find that antiderivative, then I'm simply going to add 1 to each exponent, divide by the new, plus 3, add 1 to the old exponent, divide by the new. Antiderivative of 1 is x, and always remember the plus c. With this one, sine x plus 1 over x, that antiderivative, it's an indefinite integral, so I'll just find the antiderivative. Antiderivative of sine is negative cosine x, and the antiderivative of 1 over x is the natural log of x. And don't forget the plus c. So that's what an indefinite integral is. It simply means find the antiderivative. And so when we're solving definite integrals, antiderivatives are going to come into play. This is half of the fundamental theorem of calculus. It's also called the evaluation theorem, this one part of it. And what it says is, this is the mathy definition, that if capital F is the antiderivative of little f, which means if I took the derivative of big F, you get little f, then to find the exact area under a function, you evaluate, or you find the antiderivative, then you plug in your upper limit, b, minus plug in the lower limit. So you find the antiderivative, upper limit minus lower limit, and do the algebra to clean it up, and there we go. So let's do a few. Number 1 here. It's the area under this function from 1 to 4, so I'm going to need to find the antiderivative of 2x minus 3, which is x squared minus 3x. And just to make an example, I'm going to go ahead and put the plus c in there. So x squared minus 3x plus c. Then we need to evaluate that from 1 to 4. The notation we use is we put a vertical bar at the end, and I'll put a 1 and a 4, and that means we're going to evaluate this function from 1 to 4, meaning I plug 4 in first. So it's going to be 4 squared minus 3 times 4 plus a constant minus 1 squared minus 3 times 1 plus a constant. And then I'm going to clean these up. Usually I don't simplify my functions or my answers, but I'm going to do it this time. And that would be what? 16 minus 12 plus c minus 1 minus 3 plus c. 16 minus 12 is 4 plus c. Whoops. Minus 1 minus 3 is negative 2 plus c. And what's going to end up happening here? We have 4 plus c plus 2 when I distribute the negative minus c. The c actually ends up canceling. When you evaluate a definite integral, that arbitrary constant is going to cancel, and we'll be left with 6. And 6 is the actual area under this line from 1 to 4. From now on, I'm not going to put the c in. When you have a definite integral, the plus c is not needed, because in the end, it's going to cancel out when you evaluate it and subtract the upper limit minus the lower limit. So for definite integrals, you do not need the plus c. So you do not need, that's a horrible need, whatever, plus c for definite integrals. It's not wrong if you put it in there. So if you have a hard time remembering when you should and should not use plus c, just use it for every antiderivative, because it's not wrong, but it's just not needed when you're doing definite integrals. Okay, so let's go on and let's try number 2 here. We have the area from 1 to 9 under the root of x plus 2. So let's see, I'm going to change the way that's written. 1 to 9 and root x is x to the 1/2 plus 2. And then we'll do the antiderivative. So the antiderivative of x to the 1/2, we will add 1 to the old power, x to the 3/2. And when you divide by 3/2, you multiply by 2/3. Plus the antiderivative of 2 is x, or 2x. And then we'll evaluate this from 1 to 9. So this would be, when I plug in the 9, always plug in the top number first. 2 times 9 to the 3/2 divided by 3 plus 2 times 9 minus, plug in the 1. 2 times 1 to the 3 halves, plus 2 times 1. And then I'm going to clean this up. If this is a free response question, and these are ubiquitous on the AP exam, you will probably see, I would almost guarantee you see one of these on the AP exam in the free response section. If it's free response, you can actually stop right here, but these are also all over the place on the multiple choice questions, and multiple choice questions are simplified, so you do need to be able to clean this up, which takes you back to your days of doing order of operations. 9 to the 3 halves, that's the square root of 9 cubed. So the square root of 9 is 3. 3 cubed is 27, all divided by 3, plus 2 times 9 is 18, minus 1 to any exponent is 1, so 2 times 1 over 3 plus 2. And then we'll clean this up. Let's see, 3 goes into 27 9 times, so I'm going to reduce that. We'll get 18 plus 18 is 36. Minus 2/3 plus 2. We're going to have to get a common denominator. Stinky fizzletooth. Let's see, 2/3 plus 2. I'll just leave it as 2/3 plus 2. Actually, I'm going to say minus 2/3. I'm going to distribute that negative. Minus 2/3 minus 2. And then let's get a common denominator. Pretend we're in algebra 1. This is fun. 36 times 3. Let's see, I should be able to do that in my head. 108. Yeah, 18, carry the 1, 108. So we have 108 over 3 minus 2 over 3 minus 6 over 3. That's 108 minus 2, 108. That's 180. Wah, wah. 108 minus, that's going to end up being 100 over 3. So this cleans up to 100 over 3, which is how the answer would be on a multiple choice question. However, if it is a free response question, your free response answer, please stop right here because somebody's going to make a stupid mistake and they're going to accidentally clean up wrong. So this is your free response answer. And this is your multiple choice answer. Okay, good. All right, 2 more problems I wanted to do. Let's see, area under this function from 0 to pi over 4, secant squared. You should recognize that as the derivative of tangent. Cosine is the derivative of sine, so this is going to be minus sine x. And then we will evaluate from 0 to pi over 4. So this will be the tangent of pi over 4 minus the sine of pi over 4. Plug in your upper limit first. Now minus, plug in the lower limit. Tangent 0 minus sine 0. Then we'll evaluate those. Go visit our unit circle. The tangent of pi over 4 is 1. The sine of pi over 4 is root 2 over 2, or 1 over root 2. Minus, the tangent of 0 is 0. The sine of 0 is also 0. 1 minus root 2 over 2 cleans up to 2 minus root 2 all over 2. So there we go. Last one, this is a product. There is a way to do the product rule backwards, but this problem would be a lot easier if you just expand that. So I'm going to say area from 2 to 4, and I'm going to multiply this out. That'd be x squared minus 2x minus 3. Expand all that. Now we'll do the antiderivative, x cubed over 3. Minus antiderivative of x squared of 2x is x squared. Antiderivative of 3 is 3x, and we'll evaluate this from 2 to 4. Looks like more good common denominator crap. Whose idea was it to make these problems up? All right, so let's plug in 4 cubed over 3 minus 4 squared minus 3 times 4 minus plug in 2. 2 cubed over 3 minus 2 squared minus 3 times 2. Free response question, I stop right there, even though I'm pretty sure I could do 4 cubed and 4 squared and 3 times 4. But free response, you can stop here on the AP exam. Multiple choice, we need to continue. 4 cubed is 64. 4 squared is 16. 3 times 4 is 12. I'm going to pause it while I finish this. You don't need to watch me do arithmetic. And there we go. So I cleaned it up. You have your free response answer here, and you have your multiple choice answer of 2/3. So That's it, how to find the exact area under a curve. Now that doesn't mean you can forget Riemann sums. I'm still going to ask you to solve areas or approximate areas using Riemann sums and trapezoidal rule and stuff like that. But this is how we're going to find area for the most part from here on out.